Hi everyone, I am Dr. Arindam Ghosh from the Department of Physics, Don Bosco College, Tura, Meghalaya. Today I am going to give a PowerPoint presentation on the topic Effect of Cadmium Doping on the Optical Bandgap of Zinc Oxide Nanoparticles. Zinc and cadmium form many compounds involving direct links to carbon as well as to nitrogen, sulfur, etc. But zinc appears to form more stable links with oxygen compared to cadmium. Zinc oxide belongs to a group of hexagonal wurtzite and has a wide band gap of 3.37 eV at room temperature. In my presentation, a detailed study on the structural, morphological and optical properties of CD-doped ZNO is being reported. Let me go to the experimental part now. Zinc oxide powder is prepared by co-precipitation method and cadmium chloride is used as the source of dopant. Zinc acetate is taken as the precursor, whereas ammonium hydroxide is taken as the precipitating agent. The resulting precipitate formed is collected and thoroughly washed with distilled water and ethanol constantly for the complete removal of the chlorides. Chlorides are formed as CdCl2H2O and is used as the dopant source. It is then dried in an oven for 4 hours. ZNO powder is thus obtained. Figure 1 shows the XRD patterns of undoped and CD-doped ZNO nanoparticles. Figure 1, when analyzed, reveals the polycrystalline nature of ZNO with peaks along 9 planes. The highest intensity peak is found to be along the plane 101. The crystallite size D is calculated using the Devi-Shearer formula. Table 1 shows the unit cell parameters obtained from the XRD data for all the samples. The lattice parameters A and C are found to be slightly different for CD-doped samples as compared to those of undoped ZNO. The volume of unit cell for hexagonal system, bond length L for ZNO and the parameter U in the wurtzite structure has been calculated using different formulas. Figure 2 shows the FESEM micrographs of undoped ZNO and CD-doped ZNO. A thorough analysis of the images was done using the image processing software Zen. The mismatch in crystallite size estimated from Devi-Shearer relation and that from the Williamson-Hall plot calculation is mainly ascribed to the inclusion of strain in the asynthesized sample. UV visible studies are piloted with intent of measuring the optical band gap of nanocrystals. It is found from figure 3 that there is a sharp increase in the observance of wavelength below 300 nanometer and it is due to the interband transitions at the fundamental edge. The decrease in observance with CD doping indicates broadening of the band gap. The band gap calculated by using Kubica-Monk equation from figure 4, they are found to be 3.42, 3.52 and 3.56 electron volt for undoped, 1 weight% CD dope and 3 weight% CD dope ZNO respectively. Thus it is found that CD doping increases the band gap of ZNO. From the peaks of FTIR spectra in figure 5 for undoped and CD doped ZNO, it has been established that ZNO bonding is prevalent and subsequently the vibrational mode at around 473 cm in inverse and 475 cm inverse are observed. Structural analysis endorses the formation of polycrystalline ZNO in both pure and doped forms. The crystallite size is found to reduce with increasing dopant concentration of CD. Optical studies indicates increase in the band gap with increasing dopant concentration of CD. FTIR studies reveal shifting of peaks due to introduction of dopant, which may be due to new types of vibration of crystal strain owing to incorporation of CD in the host material. The observations of CD-doped ZNO reveal that the sample exhibits properties that makes them very conducive for use in the fabrication of optoelectronic devices. Thank you.